Welcome to the HPL seminar. This is our first one for this year. Happy New Year, everyone. Hope everyone had a good holiday season and is excited to be back. Just a few quick announcements. So the first one, if you are in Case 396, you are in the right room. Please stay here. Watch the whole presentation and then stay back for your class. There's a part that follows after the presentation. So thank you for joining us. Today, we're hearing from Pearson, who is a PhD candidate in the Integrated Exercise Neurophysiology Lab under the supervision of Dr. Jalal Abu-Darda. Aaron completed his Bachelor of Science in Kinesiology with a minor in Statistics at the time in Fraser University in 2020 under the supervision of Dr. Dave Clark. Aaron then went on to do a master's in human kinetics at the University of Montreal, which he completed in 2022 under the supervision of Dr. Jonathan Tremblay. Now today, Aaron will be presenting his PhD work on fatigue-induced alterations in gait from a neurophysiologist's perspective. And one fun fact about Aaron is that he has been rehabbing his second Achilles tear within 12 months. So if you need tips on how not to or how to tear two Achilles in 12 months, reach out to Aaron.
I don't suggest doing it. Thanks, Ashna. Happy New Year. Through this rehab process, my right calf is a little weaker than my left one right now. So if I'm limping, that's why. Which is a great segue to start the talk, which is what happens with fatigue-induced running and alterations in gait. There we go. Thanks, Laura. Yeah. So typically what we see when somebody's on a prolonged run is that they will shorten their stride length, and in an attempt to maintain their speed, they will increase their stride frequency, as well as increase their ground contact time and decrease flight time. Now, there are quite a few explanations that have been proposed, one of them being metabolic, another being biochemical or perceptual, but coming from a neuromuscular and neurophysiological background, I'm going to be focusing on the neuromuscular one, which is that there's a general decrease in force production capacity of the main or primary movers. In our case today, it's going to be knee extensors and plantar flexors. We also see a development of central fatigue, and which is a decrease in central motor output, and an increase in peripheral fatigue, which is, we'll go with a general term of contractile interference in the muscle. So as we get weaker, we can't propel ourselves as hard. We have a shorter stride length, and to make up for that, we're going to increase the number of strides we take per second. So today's seminar is going to be broken up into three parts. One, just background, make sure that everyone's on the same page. The second being whether or not these changes occur concurrently. So I have some evidence that I'll present. Then we have two papers, a review paper that is submitted, and then a study that I performed, and then we'll talk about how fatigue affects gait and go over those explanations in a little bit more detail, as well as I'm going to bring a new hypothesis or an expansion on one of the explanations into the talk. So to establish our working definitions, we'll start with neuromuscular assessments. So here we're going to talk about the plantar flexors. In our lab, we can do this where we have somebody strapped down to the chair and perform a plantar flexion. So push down into the force plate as hard as they can, during which we will record force output. We'll then apply an electrical stim, so a 100 hertz doublet, which is superimposed. So that's during the max voluntary contraction. And then when we ask them to rest, we'll then stim 3 more times. So 100 hertz doublet, 10 hertz doublet, and a singlet. From there, we can calculate or quantify total neuromuscular ability, as well as the ratio between the superimposed and that first twitch being the central component, lending to our force output, which will be essentially just from central motor drive. And then the peripheral component will focus on twitch, and that's going to be at the muscle, so distal to the neuromuscular junction, and that's going to be calcium kinetics, contractile ability, sarcolemmal excitability, etc. So from there, we'll get this pre-intervention, something like this post-intervention, and we can quantify neuromuscular fatigue as a general decrease in maximal force output, the change in the ratio between superimposed and first resting twitch, as well as peripheral fatigue, which is going to be the change in resting twitch forces. In terms of gait, we have 4 parameters, just the spatiotemporal ones that we're focusing on today. Stride length, which is the distance between heel contact to heel contact of the same limb. We also have stride frequency, which is the number of consecutive strides of the same limb per second. Ground contact time is the amount of time between heel contact and toe off. And flight time is going to be the amount of time between toe off of one foot and heel contact of the other. The adaptations to running or alterations due to fatigue is going to be, in our case, a decrease in stride length. So we see that as stride length decreases, to maintain our running speed, we have to increase our stride frequency. So in this case, we have well, for example, like an entirely new stride, or an entire stride that now makes it into that stride frequency. Similarly, for ground contact time and flight time, if we increase our ground contact time, which is visualized by the increase in the larger step, we then have to decrease our flight time. That being said, these can occur concurrently. It's not mutually exclusive to just stride length and stride frequency, or just ground contact time and flight time. So, having established that, I came across some literature that kind of put me on this path, and I wanted to understand whether or not there were neuromuscular changes that happened concurrently with gait changes. Now, a lot of the literature has been on pre-post measurements, which provides you the ability to estimate or infer whether or not these occur in parallel or concurrently, but it was only in 2004 where Plass and colleagues actually invited highly trained runners to the lab and performed neuromuscular assessments before the run, as well as at hourly intervals. So these individuals ran at 55% of their max aerobic speed for 5 hours, and we have the neuromuscular responses here. And in general, the values don't really matter so much as the trends. So we see trends in overall neuromuscular fatigue, central fatigue, and peripheral, as well as what they did for the first time was also measure gait parameters at these hourly intervals. And we see, again, just a trend in stride duration, and a decreased stride duration is equivalent to an increase in stride frequency. It wasn't until 2010 and 2011 where Martin and colleagues in 2010 and Morin and colleagues from the same lab group in 2011 published a companion papers where they measured plantar flexor and knee extensor force, as well as central and peripheral fatigue over the course of 24 hours. This was 24 hours of treadmill running. And the neuromuscular parameters were measured every 4 hours. And again, we see just these trends. Downward trend in MBC, a downward trend in voluntary activation, or an increase in central fatigue and an increase in peripheral fatigue. A year later, Moran and colleagues published this, so it's the exact same protocol, but gait was assessed every 2 hours. And again, we see these trends. Stride frequency and contact time showed significant differences. Flight time showed no significant difference over time. So this provides a lot of evidence or suggests that these might occur concurrently, or at least there might be a relationship here. It wasn't until 2016 where Giandolini and colleagues invited ultramarathoners into the lab. And they were the first to actually establish or quantify the relationship between neuromuscular fatigue and gait. So a day or two before the ultramarathon, they invited these runners into the lab to perform neuromuscular assessment of the plantar flexors, as well as a gait assessment. Following that, the marathoners ran an ultramarathon, so this was mountainous, for 110 kilometers. And then an hour later, so as soon as they crossed the finish line, they had an undergraduate student pick them up, drive them to the lab, and then they performed these neuromuscular and gait assessments once again. And what was reported was this. So we see in gray are twitch forces. So we have a decrease in twitch force, which is an equivalent to an increase in peripheral fatigue, and in response, an increase in stride frequency, where the authors concluded that it was this interference in the contractile ability of the plantar flexors that led to a diminished ability to propel ourselves, and we have this increase in stride frequency. So them being the first and only ones to quantify this relationship, I wanted to know if this was unique to their study, or if this were to happen in general. So I performed a review with secondary analyses of papers that met our inclusion criteria, so they had to have performed at least one neuromuscular assessment. This was going to be of the knee extensor or plantar flexor, or both, as well as they had to have recorded at least one spatiotemporal parameter, so stride frequency or length, ground contact time, or flight time. So here, they had to be healthy individuals. They had to perform a prolonged run. And we had to have seen assessments at least pre-post, and not necessarily all the way throughout. The exclusion criteria couldn't be only uphill or downhill running. Those elicit different neuromuscular responses. So we screened 1,756 papers. We had 121 that met full text review, and we have 19 papers that met inclusion criteria. Out of that, we have approximately 300 participants with a decent range of experience level, except we do have highly experienced individuals that make up the vast majority. 3 of the studies that met inclusion criteria assessed knee extensors and plantar flexors, and then 8 assessed knee extensors and 8 assessed the plantar flexors. Since we didn't specify whether or not it had to be overground or trail running, we have these protocols, so 7 overground running protocols and 12 treadmill protocols with distances ranging from approximately 4 kilometers to 171 kilometers for a 15-minute run to a 20-hour run. So as we would expect, we have a decrease in MBC, so overall neuromuscular fatigue. We have an increase in central fatigue and peripheral fatigue, as well as these typical changes. So an increase in stride frequency, a decrease in stride length, increase in ground contact time, and decrease in flight time. So these are all values that we would anticipate seeing, and we did. And then what I did was I quantified the relationships between them. So I calculated the percent change between neuromuscular parameters and gait parameters, and then just threw them into a simple linear regression. And here we have a change in MVC, so a decrease in force output or an increase in just general neuromuscular fatigue led to an increase in stride frequency. So like Giandolini and colleagues, we see that there is a diminished ability to propel ourselves because we have less force capacity, leading to an increase in stride frequency. We then have treadmill and overground running separately here. So treadmill running, the relationship improved, where 56% of the variability in the change in stride frequency was explained by a change in neuromuscular fatigue. That being said, overground running showed a non-significant relationship, and it's quite small, but we can attribute this to a very small number of papers that actually assess both. As we would expect, there's the inverse relationship with stride length. Similar strength, R squared 0.44. A decrease in force ability leads to a decrease in stride length. But when we parse these out to overground and treadmill running, we see that these relationships improve drastically. So 80% of the variability in stride length changes are explained by the changes in force output or general neuromuscular fatigue. We then looked into flight time and ground contact time. There were no relationships with ground contact time. However, there were with flight time. So we have here only 2 studies assessed flight time following an overground intervention. So I didn't include that here, but we see 66 to 68% of the variability in the change in flight time is due to a decrease in force capacity. So this all lends evidence to that neuromuscular response, or how general neuromuscular fatigue leads to the inability to propel ourselves both horizontally and vertically. What I also found was a strong relationship between decrease in voluntary activation or an increase in central fatigue with a decrease in flight time. However, even though this is a significant relationship, we only have 6 or 7 studies that met inclusion criteria for this, and from there were only about 5 that were done on a treadmill. So in this case, I'm a little bit more weary as to whether or not these relationships are as strong as they appear to be. As well as twitch, we see twitch here. There's no significant relationship between peripheral fatigue and ground contact time. I just threw this in, so there is a relationship with ground contact time, I apologize. But we see that when we look at treadmill running only, that this relationship is extremely strong. That being said, there were 5 studies that met criteria here. So our p-value is 0.1. Again, we have to consider that a small number of papers met criteria. We don't actually know whether or not these relationships are as strong as they appear to be. So our takeaways from this review paper. Neuromuscular fatigue leads to a decrease in force output. That decrease in force output leads to an inability to propel ourselves both horizontally and vertically. Something I didn't show is that when you parse these out by muscle group, these relationships improve. I just didn't want to overwhelm you guys with plot after plot. We've got plenty of more to see later on in the lecture as it is. Evidence suggests that central fatigue affects flight time and peripheral fatigue affects ground contact time. And in the end, we need a lot more research to understand whether or not these relationships are as strong as they are, especially when it comes to central and peripheral fatigue and their relationships with gait. So biomechanists in the room, please collaborate. We'll do the neuromuscular stuff. You guys do the running. All right, so from there, I wanted to understand whether or not these relationships and these responses were the same between experienced individuals and recreationally active individuals. So this study is the only one since Giandolini and colleagues to actually quantify the relationship between neuromuscular fatigue and changes in gait. So we had individuals come into the lab 7 times, the first time being for familiarization. Then we had 2 fitness assessments, 2 runs at a higher speed, and then 2 at critical speed. We then performed neuromuscular assessments of the knee extensors, which we'll get into, rather than the plantar flexors. So here, critical speed is a speed that theoretically we can maintain indefinitely. So this is the greatest speed that can be maintained through aerobic sources only. In the 3-minute all-out test, so this is a typical trace that we see, the concept or the idea is that over the first 150 seconds, we deplete our anaerobic energy stores, and then that last 30 seconds, the mean of that last 30 seconds is our critical speed. This we did on a non-motorized treadmill, so they were tethered from behind to a pole, and it has been validated by Souza and colleagues in 2022. Cycling version of this has been validated for 15 to 20 years. So having established our critical speed, our protocol looked like this. So Giandolini and colleagues are up there just as a comparison. We did neuromuscular fatigue assessments of the knee extensors. Approximately 5 minutes later, rather than a day or 2 later, we had them running on our non-motorized treadmill at 10% above critical speed or at critical speed. And then through a lot of training with our participants, we were able to get them from the treadmill to the chair, performing that max voluntary contraction within about 30 seconds. So here I have some relationships at the higher speed, so critical speed plus 10%, and we see that overall, this relationship is 0.44, so very similar to what we saw in the review paper of mine. And the individual sessions, we have similar outcomes. We also have a relationship between stride length and twitch force. So a decrease in twitch force, so it's an increase in peripheral fatigue, actually led to an increase in stride length, which I'll discuss shortly. And these relationships were stronger in the visit 5, so the second time that they performed this assessment. When running at critical speed, we have this relationship here. So black is all data amalgamated between the 2 visits, and it explains, or what happens is that 64% of the variability in changes in stride length in this case are explained by changes in neuromuscular fatigue or overall force output. Interestingly though, that relationship is mostly driven by one of the visits, so visit 6, rather than visit 7, which we believe may be due to a learning effect, but we can't quantify that, so I have no way to state that concretely. So here, takeaway, MVC, change in MVC explains 45 to 65% of the variability in changes in stride length, which is similar to what we saw in the review paper and a little bit stronger than what we saw in the paper published by Giandolini and colleagues. However, these associations are inverse between the run at critical speed and above. So I'll just back up here. We see that as individuals got weaker, or as neuromuscular fatigue developed, we actually see an increase in stride length. Whereas when they were running at critical speed, a decrease in force output or an increase in neuromuscular fatigue led to a decrease in stride length. So this is inverse, and we believe that's due to a change in running posture. So at the higher speed, our runners adopted a more mid and forefoot running stride. And there's a lot of literature out there, from what I've read, stating that forefoot runners will typically decrease their stride frequency, whereas rear foot runners will typically increase their stride frequency. So we believe that's what's going on, but I'm open to any of your opinions. So we have this, oh, sorry, going the wrong way here. There we go. So there are different mechanisms that are associated with the running protocols, and it appears to be intensity dependent. And this is probably due to different neuromuscular adaptations or mechanisms that are going on. So now, in the end, why does fatigue-induced running, or running-induced fatigue rather, lead to changes in gait? So current explanations, to minimize energy cost, so metabolic, to mitigate muscle damage, pain, and perceived effort, a decreased propulsive ability, which is what I've been discussing, and an expansion or a hypothesis of mine being that we have to actually take into account work redistribution to bridge that gap. And that is going to be where a little bit more neurophysiology actually comes into play. So a lot of literature will say that our changes in gait are due to our reorganization to minimize energy expenditure. And while this seems intuitive, we do also know that energy expenditure goes up over time. So when I looked into it, we found that there's no relationship between a change in energy expenditure, so an increase in energy expenditure, and changes in either stride length or stride frequency. So although this explanation seems intuitive, there's no evidence that I have found to support this. Next is to mitigate pain and muscle damage. So with each stride at initial ground contact, there's an eccentric contraction, which will lead to a little bit of muscle damage and pain that's perceived. But at what point does this muscle damage, pain, or effort result in changes in gait? And from everything that I've found, there are no relationships there. However, I haven't been able to find concrete literature that looked into these relationships in the first place. And then the neuromuscular standpoint or concept is that a decrease in maximal voluntary contraction force, so overall neuromuscular fatigue, will lead to a decreased propulsive capacity. However, this doesn't take into account anything, any underpinning mechanism. So no peripheral fatigue or central fatigue is included within this explanation. And this is where my hypothesis begins. But we first need to cover what the sensory tolerance limit is. And this is the more neurophysiology side. So the theory is that we can only handle so much afferent and efferent signaling. We have an upper threshold. And as we have more afferent signals that come into the brain, we have to decrease the amount of efferent signaling out. When we hit that threshold, we have three outcomes that are possible. Task termination, so you stop. You're going to alter your pacing, so you're going to slow down, but let's say you're running on a treadmill and it's at a constant speed. Well, you might want to alter your movement strategy. So in the end, to sustain a running speed, you have to somehow offset these inputs and outputs. So as afferent feedback increases, which comes from peripheral components, we then see a decrease in efferent feed-forward signals, or a decrease in central motor output, which would lead to an increase in central fatigue. That then will tie into joint work redistribution, which we know is, or we can think more colloquially as demands placed on that joint. So the ankle joint will have less demand, or rather the plantar flexors put less demand on the ankle over time. And we see that that will move that work proximally to the knee. So the knee extensors have more of a demand, and the hip extensors also have more of a demand over time. Now this, just like what we saw with the neuromuscular adaptations were progressive, well, we also see this. So in blue is work at the ankle, positive work at the ankle. Green and red are hip and knee. So how does this all come together? Over time, we see that there's an increase in peripheral fatigue of the plantar flexors. So we see that more afferent signaling coming in due to metabolic waste. This leads to decreased muscle contractility and the overall inability to actually contract the muscle. This also will then increase our contraction time of the plantar flexors. This leads to a proximal change or a change in work from the ankle to the knee, placing more stress on those knee extensors. And we will then see a greater development of central fatigue from the knee extensors. So we have this large increase in afferent firing, and to offset that, we have a decrease in efferent firing. So more in, less out. So in terms of spatiotemporal parameters, how those are changed, we have an increase in plantar flexion contraction time. This leads to a greater ground contact time and a decreased flight time, and a decrease in knee extensor propulsive capacity, which leads to a decrease in stride length and an increase in stride frequency. So in conclusion, running-induced fatigue is due to neuromuscular components, general neuromuscular fatigue, as well as central and peripheral components, as well as running biomechanics, which we focused primarily on spatiotemporal parameters. I found that neuromuscular fatigue in general explained anywhere from 45 to 65% of the variability and change in stride length and stride frequency, and 70% approximately of the variability in changes in flight time. And then, in general, as neurophysiologists, we have to consider work redistribution, which is something that I haven't seen in the literature as of yet. And that's something that actually we're looking into right now, is how do these central and peripheral components or central and peripheral fatigue lead to work redistribution and overall changes in gait. So on that note, I want to thank my co-supervisors, lab mates, two of them that couldn't be at CSEP. Well, actually one didn't make it into the picture though. The undergrads that helped me, Deep Lab, for sharing their space, and everyone else that put up with me coming over to their offices all the time and asking questions. On that note, I'll open up the floor to any questions you may have.
Thank you. Actually, I'm familiar with the post-activation potentiation, which is like you induce a twitch before the activation, you activate the muscles and you look at the twitch after, and the twitch after, not the twitch. Yeah, like stimulation, and then it's increased after. So I'm wondering why you can do a re-activation stimulation, because the mechanism for this is a phosphorylation of the myosin light chain. And do you think this might have changed, like per se, might have changed during fatigue, running, and this might have affected how much the post-activation is increasing, and then your like the ratio between the stimulation that you do during the MVC and the stimulation afterwards will change just because of the phosphorylation that is becoming different.
Can you summarize that in like a sentence or two, please?
So What do you think the effect of post-activation potentiation on your results on the neuromuscular fatigue, like the central fatigue, and why you didn't do a deactivate, like a twitch before activation?
Okay, oh, so you're talking just the neuromuscular assessments. I haven't seen anything that would state that there's a lot of difference in central component, or like that quantification of voluntary activation. But this is also a protocol that we use that's just standardized in our lab. Whether or not that would have changed the strength of the relationship, I have no idea. If it did, I don't think it would change it all that much. I don't know if that answered your question.
Thanks, Aaron. Got a few questions, but I'm not gonna steal all the time. So the assumption is that you get neuromuscular fatigue, so you can't generate as much force, so you can't propel yourself forward, so stride length isn't as long, stride frequency goes up to the same speed. What do you know about the amount of force you need to generate when you're running compared to the maximum force that you're generating during the neuromuscular fatigue assessment?
Yeah, so these are submaximal contractions during running, especially prolonged running. This isn't sprinting where it'd be near or closer to maximal versus MVCs are with maximal intent. That being said, from what I understand, essentially you're just shifting. So a decrease in MVC will also result in like a decrease in force output even at submaximal levels.
How do you test that? How do you?
You infer. Yeah, that's something that we've been looking into and trying to explain. I've had conversations where it could be like an isokinetic assessment and we're moving at similar angular velocities as, let's say, knee extensors during running, but that I don't have a solid answer for you on that one.
The other question I had was in your regression analyses, you've got lots of cases where it seemed like the stride frequencies or it seemed like people were being fatigued and increasing their stride frequency.
Yes.
Sorry, decreasing their stride frequency. You have people
Yes.
on both sides of that line. And then you showed the analysis where you separated by treadmill versus overground. And
Right.
it looked like in all the cases where people actually increase their stride length when they become fatigued, they're on a treadmill. Which makes sense because you can cheat on the treadmill, I think. None of this is my question.
Oh, okay, so I'll stop there.
How are people assessing these spatial temporal variables in the fatigue state over ground? Are people running at a fixed speed?
Some of
Or
them
are they allowing speed to change? Because if there are these changes in stride frequency and stride length, they don't really mean anything.
Yeah, so only one study that met inclusion criteria in those, in that review had assessments performed at 2 speeds. That was included solely because it didn't actually change the outcome of the relationships. But everything else or everyone else assessed through like speed gates or over like 15 meters, 20 meters, and they had to be within a certain percentage.
But if it's biomechanical.
Either or. So they might have done like a marathon
Okay.
and done treadmill assessments like Gianelli and colleagues. They did treadmill assessments, but overground running. Some were overground assessments, but treadmill running.
Okay, last question. Oh, okay, very, very quickly, last question. If you're in a non-fatigue state and you increase your cadence in running, the metabolic cost goes up. So why would somebody think that increasing cadence in a fatigue state would be a good way to, I don't know.
Well, I think it's not necessarily, so I'll assume that it's on a treadmill. Why would somebody assume that increasing cadence in a fatigue state would lead to
One of your
minimal
explanations
energy
was that
expenditure?
certain biomechanical changes are done to,
Oh, minimize,
minimize the energetic
right.
loss.
I think, okay, so this is personal, this is what I believe happened was at some point, so we know that we try to self-organize to minimize energy expenditure. It's not, we don't run at our optimal stride frequency, but quite close. And I think this is conjecture that at some point, somebody took that concept and said, okay, we organize ourselves to minimize energy expenditure here and now, so that must be what happens, like over the course of a run. But I don't have a good answer for you on that one. That answer, or that explanation I've seen mostly in biomechanical research.
Another question. Benefits, and then Walter.
Could you go to the second slide, please?
Yeah, hold on. All right. Getting there.
What is that signal?
So,
The noisy signal, what is that?
oh, that's ENG.
That force?
That's ENG activity.
EMG?
Yeah.
And the right-hand side of that curve, is that EMG two or is that force?
Over here?
Yeah.
Well, that's, so this signal is going to be what's picked up from the electrical stim.
The EMG two.
Yes, yeah, it would be ENG. But this is not muscular, this is due to our artificial stim that we're applying.
And then you basically compare that to some microscopic changes, like stride length and
Yes,
stride frequency and so on.
yeah,
But you never go back to analyze the EMG signal, correct?
correct.
By
From our standpoint, there's a very weak relationship between ENG activity and force output.
so you don't think that you could change the force output by changing the frequency of the signal?
Are you talking about the stimulation intensity
Or
or
the
ENG?
frequency of the actual EMG signal?
I'm not, so if we increase ENG activity. I'm not,
The question is, do you believe that, you said that you don't think that EMG is indicative of the force output?
right,
And so I think the follow-up is, you don't think that the frequency change in the EMG would result in a change in the force?
so it depends is the answer. If you're performing a max voluntary contraction and you're going to sustain that contraction, we'll see EMG activity trend downwards over time. If we're performing a submaximal contraction, EMG activity will trend upwards over time. So I don't have a good answer for you on that, in terms of changing EMG activity and force output.
Since you're on that slide, I was curious about why did you change from doublet 100 hertz to 10 hertz to twitch?
Each of them tells us something different. So the 10 hertz doublet, we believe tells us about calcium kinetics. And what we see is this is going to be at a normal firing frequency for action potentials. 100 hertz is beyond our normal firing frequency, but we believe that at the 100 hertz doublet, this will essentially, like, it's maximizing calcium sensitivity and output, let's say from the sarcoplasmic reticulum. So we take the ratio between the 10 hertz and 100 hertz to understand how, say, like efficient our calcium kinetics are. Twitch is going to incorporate that as well as like sarcolemmal excitability, phosphate handling, stuff like that.
So is this actual data?
Yeah, well, this is pulled from the ESSA paper, by,
Because I'm surprised, because normally when you give a doublet, you get enormously high force. And at 10 hertz, I would expect a much smaller force. And then also, there seems to be a time delay between one and the other,
yeah, so there's about 2 or 3 seconds between,
not just 2 or 3 seconds.
Yeah.
Because that's what Venus was alluding to, that you have to be very careful with your twitches after the stimulation, because, you get that potentiation that you was talking about, that decreases quite quickly. So if you give the twitch 3 seconds after, or 7 seconds after, or 10 seconds after, you get a distinct decrease in the twitch.
yes.
You account for that by very carefully timing when you give the twitches.
Yeah, we use a computer program, so it's always the same intervals.
So do you have an explanation why a doublet normally will give you twice as much force as a doublet with 10 hertz, but in that particular situation, you don't seem to have that?
I don't think I've seen anything where the 100 hertz is that much larger than 10 hertz. Even from my own data, and others in the lab, they're usually somewhat similar.
There's some fabulous data by Burke, but it's not done in human muscle, it's done in cat muscle, where it shows this enormous increase when you give a doublet stimulation, which has a pulse interval of about, 7 to 10 milliseconds, and I guess with 100 hertz, you have a 10 milliseconds, so that's, do you do muscle stimulation or nerve stimulation?
Nerve. So this would be, well, let's say for the knee extensors, it would be femoral nerve.
Yeah.
In this case, it would be peroneal.
And then the other question I have with respect to this, we did some work a long time ago on superimposed twitch singlet, doublets and triplets and so, and we found enormous variability. That, you can ask, but what we did is people, we had them do 10% of maximum voluntary contraction, 20, 30, 40, 60, and so on. And sometimes at 60% of maximum voluntary contraction, we didn't see a superimposed twitch. And sometimes at 100% maximum voluntary contraction, we saw the superimposed twitch and it was enormously variable. Do you have that at all, or?
Well, we will only ask people, like, we'll only stim at 100%.
Yeah.
At an MVC. But yes, I have looked into it. That's going to affect like our voluntary activation calculation. And there are plenty of issues when it comes to voluntary activation. But we will standardize it to stim only at, like during an MVC. And we'll typically only analyze the data if we calculate that voluntary activation is above 85% or so.
So when you get a bigger value, you eliminate that.
Yes.
Yeah, our.
I have a comment and a question. So first of all, I think you made a very good point that we don't know whether in the fatigue state, people are at optimal or not optimal, stuff like the frequency. But I just want to suggest maybe that's a study worth doing because it would be relatively easy. Because you guys are well set up for doing fatigue studies. You just have to, have force people to use different subfrequencies surrounding the curve. So I would just suggest you or someone else to do that.
Okay.
Well, worth doing.
Yeah, I mean, I've seen a bit of research on like 10% above, 5% above optimal, and then 5 and 10% below. I don't have the results.
Oh, okay.
Top of mind though.
Okay, so here's my question. It seems like your measurements, central and peripheral fatigue, are what you base much of your hypothesis on. But then to me, it seems like this idea of sensory overload comes out of nowhere. So where does that come from when you're measuring peripheral and central, basically efferent kinds of things?
So, I'm not sure I understand the question. Like the sensory tolerance limit in terms of prolonged running. So what we saw was that peripheral fatigue will develop at a much faster rate in the plantar flexors. So this leads to a huge amount of afferent firing. Because we have a certain threshold, we're going to have to compensate or even that out. And in doing so, we have a decreased central motor output, central drive, and that will mostly affect the knee extensors. So the knee extensors will develop central fatigue much faster, whereas plantar flexors develop peripheral fatigue at a much faster rate.
Well, what's the data on this afferent overload?
It's mostly in cycling and it's based on afferent blocks. So an epidural is performed and then they look at like exercise performance and task duration. So it's an assumption or an inference. It's our best guess right now.
Well, I guess I would suggest if your hypothesis is about this sensory threshold, then maybe you can do a measurement that's related to the sensories as well. I guess an example would be you could do like an H reflex or something. And then if you tie together various reflex kinds of things with what you're also doing with central and peripheral, then I feel like you can tell a story rather than inferring, because it's kind of an inference on what's not there, as opposed, because you are measuring objective information. So isn't there a way to get objective information about that sensory aspect, or do an epidural or whatever?
Yeah, I mean, I don't have access to, epidurals. Fentanyl is very well controlled. So
Okay, but you can do stress reflexes, you can do H reflexes.
yeah, the issue with like H reflex and those they're very sensitive to movement. So they're very finicky. So there's only so much validity to those measures. And that's why we don't really do them anymore in like neurophysiology labs.
I think Osman had a question and then I'll.
It's more like a comment based on what I said. You can do maybe vibration assessment like Brian Peter does. You vibrate the fatigue muscle and then you measure the EMG and look at the correlation in between. Maybe a fatigue muscle is going to have less correlation with the input compared to a non-fatigue muscle, and it's less sensitive to movement. You can do it within the movement. What you said about H reflex is very true. It's very variable and movement really affects it, but another way might be applying some vibration to the muscle and measuring EMG after and before fatigue. That would work.
Thanks. Appreciate it.
Walter had a question.
Yeah, I wanted to come back to what Art said as well, because I have the same question. And I'm not sure if I understood it fully, because we know, we talked about that when you run at our normal stride lengths and you go, 5% longer, 5% shorter at a given speed, then it seems energy cost goes up. And so did you say that people have done that also in the fatigued state? So you have people run 100 kilometers, the stride lengths that they prefer is shorter. And then you perturb that stride length and then up 5% longer, 5% shorter. Would oxygen consumption go up? Or would it go down because optimal stride length is always the same? Or optimal stride length actually changes in terms of efficiency when you're fatigued?
I don't know.
Has nobody done that?
I would have to go back and look at some of the papers that I have. I believe I have one paper that has looked at we'll call it prolonged running, but I don't believe the intervention was very long.
That would be kind of my hypothesis actually, that with the new capacity of the muscles that you have, you still kind of, in an endurance sport like you're looking at, that you still try to minimize energy, but your energy might be minimized with different mechanics, there was a different stride length, different stride frequency. Because
Yeah.
when Jim Hay was here, he looked at exactly that in a variety of different sports. And, you know, like in rowing and in cross-country skiing and in swimming, and everybody seems to do that when they get tired. Everybody seems to take faster strokes, faster strides, but not quite as long if they want to maintain speed. So it doesn't seem to be a running thing. It seems to be an overall adaptation speed thing that seems to be happening in a lot of different sports.
Yeah, I think it's just evolution in general. We want to minimize energy expenditure in whatever we do. So yes, over time, we do want to minimize energy expenditure by adjusting our gait, but that still doesn't explain that doesn't necessarily explain why we change our gait. Is just energy expenditure. I think there are too many confounding factors there.
I like the work distribution thing, you know, you say, oh, you might do a little bit more with the hip or the ankle or whatever. And have you tried to quantify how that, you know, from a movement pattern looks, or very simplistically, do people change, you know, footfall patterns, for example, which would be something very obvious when they get more fatigued?
Yeah, so that's what we're looking into now, is prolonged running with knee extensor and plantar flexor, and then it's on an instrumented treadmill. So we're able to collect like foot strike pattern, as the spatiotemporal parameters and like spring mass model parameters as well, but we just started, so I have nothing to present on that.
The other thing that I was thinking, you know, after about 2 hours, you know, roughly in a marathon for good runners, you seem to be running out of glycogen. And then you have very different energy sources available for movement, for running. Is there potentially a distinct difference in how you adapt when you have glycogen available compared to when you don't have glycogen available anymore, or did anybody look at that?
That I don't know if anyone's looked into. But what I can say is like, the adaptations are going to be similar, of a similar magnitude between inexperienced and experienced runners. It's just a matter of when that happens. So inexperienced runners will typically see the changes in gait earlier than experienced runners. And that might be due to just like running efficiency or economy, but we also know that the more experienced the runner is, the higher proportion of utilization of fats that they'll use versus like glycogen stores. So I don't know, I mean, from a neuromuscular standpoint, that change is fairly concurrent and it's just a matter of duration, like when that happens.
I'm not sure if you watched Eliud Kipchoge break 2 hours in the marathon distance when he did that. And the first time he did it, he didn't quite break it. It was like 19 or 20 seconds too slow. And I thought it was absolutely incredible how he ran 252 kilometers for 35 kilometers. And then he got fatigued. And then he ran 3 or 4 seconds slower. So he ran 255, 256, 257 per kilometer. And I thought it was amazing how you didn't really see anything, but all of a sudden he was imperceptibly slower, and without a stopwatch you wouldn't really see it. But clearly the fatigue was there, and he lost those 20 seconds in the last 6-7 kilometers by just being 2 or 3 seconds slower per kilometer. So what would you guess happened there?
I think he got tired.
I'm sure.
But so
In terms of stride length, stride frequency, I mean, you know, do you think there was a?
yeah, so I'll go back to like critical speed for a second. Critical speed is the max speed that we can maintain purely aerobically, hypothetically. But we know that after half an hour in less trained individuals and up to an hour, hour and a half in well-trained individuals, that holds true. And then there are general inefficiencies that will build up. So we have metabolite buildup, we have dehydration, glycogen store depletion, that occurs at, let's say, that hour and a half mark. So you're not as metabolically efficient. So I don't know, because of all these occurring at a faster and faster rate after that hour and a half, that might lead to like an increase in that afferent firing, decrease in central motor output, and then that leads to your stride length shortening, even if it's just slightly. That would be my take. Apart from like effort and pain, which play a fairly large role in terms of like motivation to continue running at that speed.
One thing that happens, of course, as well, is that your stance time gets longer. And I wonder if ever anybody measured the rate of force increase, in the fatigued and the non-fatigued state, that my hunch would be it's a little bit slower. And maybe you take, maybe you stay on the ground longer because you need a little bit more time.
Yeah.
To produce that force, and then that changes the whole way you run.
Yes, yeah, absolutely. And it's the longer the contraction time, the more metabolically efficient it is as well. So it costs a little bit less energy, but that all kind of plays into changes in gait.
I have a quick question or suggestion here. How long is your protocol that you ran? And you said you were measuring changes in stride frequency now with the upcoming protocol, and you have the instrumental treadmill.
Yeah, so the runs at like critical speed plus 10% were anywhere from 5 to 15 minutes, maybe 20 minutes. At critical speed, it was closer to about 15 minutes to an hour or so.
Do you know with critical speed, how it relates to like percent of lactate threshold speeds or heart rate reserve speed?
So critical speed is at second, like in theory at second threshold.
Oh,
Yeah, so it's speed at second threshold.
why I asked the question is we've done a study with a prolonged run, 2 hours with highly trained runners that were training for a marathon or having just ran one. And we didn't see any work redistribution in terms of the 2 hour long run or changes in a lot of the parameters that we had expected or hypothesized to see. So I'm wondering, and that was for an AFT study. So I'm wondering if AFTs did something to mitigate that redistribution or fatigue-induced changes, or if things change when you go from trained or untrained, which is something you also said was part of the.
Yeah, I don't know.
Maybe something we can chat about because.
Yeah.
Yeah, I'd be curious to see if you find changes or not, because it was surprising to us.
Yeah. I mean, there's just human variability in general, so.
Do you measure EMG and oxygen uptake in your test?
We didn't, with the next study, we will.
That,
That was great, thanks, Eric. Just curious, like, getting at, trying to disentangle maybe what some of your research questions are and hypotheses, I'm wondering how, does the literature ever look at this in the context of training studies? As in you take a cohort of people and you examine them over time as they become more well-trained, are there any clues there that help?
There are definitely training intervention studies. We see that gait adaptations are slower, but typically, from what I understand, a training intervention will also just lead to increases in strength. So is it that these changes in gait are slower, or is it also just because somebody got stronger and then that affects the slope of the change or rate of change? So I don't know. I don't know if there's any good distinction between, like what the adaptations are from a training intervention and their effects on gait and neuromuscular fatigue in general.
All right, thank you, Erin, for that talk. With that, we'll thank you again.